right, section 1.4, shifting, reflecting, and stretching graphs. The first thing that you need to know is that there are 6 very common functions, and you need to be comfortable with those functions. You need to kind of know them by their name. You have to have an idea of what the graphs look like. So if you have a function, f of x is just equal to some number, f of x is equal to c, where c is some real number, that's called a constant function. That's just like having y equals 5. If it's y equals 5, you guys know you have a line, a horizontal line. I'm going to change my color here. All right, so there's also the identity function, and the identity function just means that the x's and the y's are identical to each other. So f of x is equal to x. So if f of x is equal to x, that just means you're graphing y equals x. If you're graphing y equals x, every x is equal to its y value on that line. So if you pick an x value of 1, it's equal to a y value of 1. If you pick an x value of, say, -3 and you read down to the graph, you're also going to get a y value of -3. That's the identity function. F of x is equal to x. You also should be comfortable with the absolute value function. The absolute value function looks like what would you guys say would describe the absolute value function?
A V.
A V, yeah. Looks like a V. F of x is equal to the absolute value of x. Remember when you're typing in the absolute value of x, I believe you press math and then you go to the right to num, and it's the very first option. It says ABS, abs, meaning absolute value. Looks like a V-shaped graph. The square root function, f of x is equal to the square root of x. You always start at 0, and then it heads to the right. You don't take square roots of negative numbers, so it only contains the positive x values. Now this has come up a couple of times before too. Why is the graph not down here? In order for the graph to be contained below the x-axis also, you would actually have to be graphing f of x is equal to positive and negative square root of x, which we are not. We are only graphing f of x is equal to 2x. So if I do throw a positive and negative in front of it, you know you need to contain the bottom part of the graph too. All right, quadratic function. You guys have used quadratic functions over and over and over again, so that should not be a big deal. F of x is equal to x squared. That's a parabola, quadratic function. You guys know what a parabola looks like. And then, of course, f of x is equal to x cubed. That is a cubic function. Looks kind of like a curvy, kind of like an S. All right. Next page, page 2. Vertical and horizontal shifts. Some of this is going to be kind of review. Some of it might be new. All right, a vertical shift. If you move something up c units, if you move it up c units, all you need to do is take the value of the function, then you add c to it. F of x plus c, that's going to move it up. If you're going to move it down, a vertical shift, if you are moving it down, you're going to, of course, subtract c at the end. You take your value function, the value of the function, you subtract c from it. A horizontal shift. All right, this is a little bit trickier. If you are going to move it horizontally c units to the right, you would think that you would add on to the c. But when it's in a horizontal shift, you always do exactly the opposite of what it says. So if you need to move it c units to the right, you take the value of x and you subtract c from it. Notice that the x value shows up, the x minus c show up in a set of parentheses, and I'll go through a couple of examples what I mean about that in just a minute. If you are doing a horizontal shift, c units to the left, well, a left shift is a negative shift, but you have to add c to it instead of subtract c, and that seems a little confusing, but you've actually done that before, believe it or not. Just like when you're finding a 0. If you're finding a 0 and the factors are x minus 2 times x plus 3, that's finding where a graph crosses the x-axis, and it's actually a parabola that's shifted a little bit to the left or a little bit to the right, and it always ends up being exactly the opposite of what you think it might be. So the 0 here would be 2, The 0 here would be a negative 3. So notice the parentheses means it's going to be the opposite of that value. Examples, f of x is equal to x squared. So I wrote down the common function, f of x equals x squared. I graphed it for you, but then what am I asking you to do here? What kind of a shift is this? F of x minus 3 is what kind of a shift? It's a vertical shift because you're subtracting 3 at the end. It would be horizontal if the minus 3 showed up inside the parentheses next to the x, okay? So if it says minus 3 at the end, that is a vertical shift. That is this parabola, the common parabola, shifted down 3 units. This one over here, f of x minus 3. Well, remember if it's minus 3 inside the parentheses, that means it's going to shift in the opposite direction of what you might think. So it says minus 3, you actually are going to shift it 3 units to the right. And that is, now if the parentheses were not around the x minus 3, then it would end up being another vertical shift down 3 units. So this parabola, again, I went back to the common parabola, and I shifted it to the right 3 units. Example 2, f of x is equal to the absolute value of x. I drew the common function. Now there's 2 things going on with this one. Notice the absolute value bars. And I put an x plus 2 in the middle of it. What is that plus 2 going to do to the graph?
Change it.
It's going to shift it to the left. And it's shifting it to the left because it's like inside. These aren't parentheses in this case. They're absolute value bars. But it will shift it to the opposite direction that you might think. And then the minus 1 is outside of the parentheses. If it's outside the parentheses, it does exactly what it says it's supposed to. It's supposed to shift it down 1 unit. Okay? All right, reflecting. If you reflect something over the x-axis, reflect it over the x-axis. All you need to do, for example, you have a parabola, just the basic y equals x squared, f of x equals x squared. If you're going to flip it over the x-axis, you literally just take every point on it and you make it equal distance away from the x-axis. You put a point here. You do this over here. So what you're doing is flipping it over. You're taking the opposite of the original function. And then if you're going to reflect it over the y-axis, you have to take all of the x values, replace them with the opposite of the x values that you already have, and then you will get a reflection over the x-axis. Now in this case, if I reflected my original parabola over the y-axis, the entire thing would flip and it would look exactly the same way as it does right now. So this is probably a poor example of that, but we will try an example in just a second. All right, so an example, f of x is equal to x cubed over the x-axis. Remember, if you're going to reflect over the x-axis, you just take the opposite of the function, negative f of x. So if the original function is x cubed, to graph a reflection of it over the x-axis, you throw a negative sign in front of your x cubed. So you have negative x cubed. And when you do that, when you're reflecting over the x-axis, every point in our original function, remember, just gets reflected. It's equal distance away from the x-axis, just below the x-axis. So that point would go there. This point right here would end up right here. This point right here would end up right here. This point would end up here, and when you do that, when you connect your point, you are going to end up with this graph right here, which I'm confusing myself, which direction I was going there. We end up with that graph right here. So every point is reflected over the x-axis. If you're going to reflect it over the y-axis, you have to go in and you actually have to replace your x value, just your x's individually, with the opposite of what you're starting with. Now, in this case, when you reflect it over the y-axis, it again happened, another not good example of when it's reflected over the y-axis. Again, when this happens, you end up with exactly what happens when you reflect over the x-axis. It is different than your original function over here, but it looks exactly the same way as it does over the x-axis. So I think I put a note over here, same in this case, but it's not always going to be like that. Non-rigid transformations. So in other words, you're shrinking it or stretching it. When I say stretching it, it's like you're pulling it this way. A vertical stretch or shrink just means you take the value of the function, instead of just making it the opposite of what it was to begin with, you multiply everything by some value of c, meaning some constant number like 5 or 10 or a half or something. You just multiply everything in the function by c. And if you are going to do a horizontal stretch or shrink, that means you pull it this way, then you actually multiply the x's by c. Not the entire function, just each individual x by some c value, some real value c. So a couple of examples of that. F of x equals x squared plus 2. So if you're going to do a horizontal stretch, remember you have to take all the x values and multiply them by some constant. So in this case, what I'm asking you to do is replace the x in our original function, replace it with 3x. So we're doing a horizontal stretch. It's going to be 3 times bigger. So we're going to take every x value. Everywhere you see an x, you have to replace it with 3x. So I take the x squared from our original function and I replace it with 3x. So we have 3x squared, and then you add 2 onto it at the end. When you square 3x, you get 9x squared. Notice the 2 did not change. So when that happens, you actually get the exact same graph that you started with, except now it is much skinnier. The graph is what it almost like starts to hug the y-axis. Now a vertical stretch in this case, I'm multiplying everything by 3, not just the x values. So the graph does end up being skinnier, but it also shifts the graph up to 6 rather than at 3. So vertical stretch, we're multiplying everything by 3. So our original function, remember, was x squared plus 2. If it was x squared plus 2, if it's x squared plus 2, you need to multiply that entire function, x squared plus 2, by 3. The 3 is outside of the value of the function. So we're going to take 3 times x squared plus 2. I distribute the 3 in, giving me 3x squared plus 6. My parabola gets shifted up 6 units rather than 2 units. And it is not quite as skinny as it was in this picture right here, but it is still skinnier than the original parabola. Because now we have a 3